Right, good morning. My name is Paul Kent. I'm a long-time person at SAS. I've been there nearly 30 years, which is kind of strange for our industry, for one person to live, I'll move away from that a little bit, one person to live at the same company for that long, but of course my job hadn't been the same for 30 years. And recently I've been the person who's leading our charge into taking the SAS algorithms, the mathematics, and mating it up with the more modern data environments. So we started this journey on Teradata and Greenplum and the massively parallel databases, but either we were lucky or we were cunning. Our approach is transportable and adaptable, and along came Hadoop, and it was a really nice marriage of our ideas and the capacities that Hadoop provides. So my talk is a little bit about how SAS uses a Hadoop cluster, but actually it's more about how SAS tries to be a good citizen on your cluster and interoperates with all the other things on the cluster. Data in SAS format with other tools, and how do other tools, how does SAS accept data in the format of other tools. So it's more of an interoperability talk than a straight pitch about what the capabilities of SAS on your cluster are. You know, we're kind of the new kids to the block. We're not open source, we're ISV. So getting the word out about our capabilities is not as easy as just put a web page and hope a mailing list develops. But thanks for coming to the talk anyway. So, you know, my talk is structured a little bit like this. Two ways to push the work down into your cluster from your SAS programs. One way is to translate it into SQL, and actually that's the bad way. There's a much better way that we think that we've worked on really hard over the last couple of years, which is for us to have rewritten key parts of SAS and make that available on your cluster, and then it's a collaboration between your SAS script on some SAS server, recognizing, oh, this work can be done in the cluster, and instead of doing the work on the SAS server, schedule the work into the cluster and wait for it to be done there, and take advantage of all the extra resources and the data parallelism that you find in a cluster. So I talk about those two different approaches. But like I said, I don't want to overdo that. I want to talk about the data implications of, you may have your data on your cluster already stored in many different formats, and how is SAS going to deal with that. Or you may have your data stored in SAS format, but you need to share it with other tools, and what are the options that we're providing for you to do that. And the last slide, a little bit about what's different between Hadoop and the HDFS, the Hadoop file system, and the traditional enterprise data warehouses. Which one is better for which kind of task? Is it an either or is it an and? Is it a both? Is it a some today and not all tomorrow? A lot of questions in people's minds about. Put my 2 cents on that. So I use this little arrow to try and remind myself more than anything where I am in the talk, but as I go to, I'll come back to this page and the arrow will move, and that means I'm moving on to the next topic. But, you know, using SQL with SAS is something that we have a great model for. SAS has connected to all kinds of relational databases with our live name statement, and you know, you make up a word. Ollie is my humorous live name. You know, I want to see all the data that's in my Hadoop cluster. I'll call it Ollie. And I identify my server, and I may have to log on and give a password, or hopefully my admin has set up the Kerberos and the single sign-on, and I don't have to do that in my programs. But anyway, point at your server, and then SAS actually treats all of the tables in that server as if they were SAS resources. You can see them, and you can do SAS techniques on the tables in that server. And this same approach translates when your SAS data is in a Hadoop, when your data is in a Hadoop cluster and you want to process it with SAS. Got a slide with lots of builds here. It's somebody typing in their program. You know, they run some procedure, proc x, y, z, z, y, data equals, and some table from their Hadoop cluster. So the Hadoop access method, this green box is your SAS session. It might be running on your laptop, or it might be running on your server that you log into to use SAS, but it's not running on the cluster. So your SAS language isn't interpreted on the cluster yet, but every now and then it makes connection to the cluster to go and either fetch data or to move work into the cluster. But in this case, it uses the Hive component of Hadoop to fetch the rows from that table. You know, the cluster is going to say, select all the rows from the table and break that work into all of the slices of data. So possibly Hive has generated a MapReduce job to go and fetch the rows. The those rows are brought into the memory of the computer, and unfortunately, they go all the way back through the wires back to your SAS server. So that's not a very great setup for processing big data sets in a Hadoop cluster. How could we improve that? Well, the first thing to say is, well, don't do big data sets, do medium and small data sets. But why would you do it on a Hadoop cluster if that's what you're after? So what techniques can we use to keep the most of the data in the cluster and only bring some of the data back to your SAS session? So the first thing that we've done is using SQL. We call it SQL pass-through. So many of the procedures, well, a handful of the procedures, there's an alternative way to do the work in SQL language. So proc means is a SAS procedure that calculates descriptive statistics, totals, averages, standard deviations, that kind of thing. And you can do a by statement in SAS, which means I want it for each level of a variable or a couple of variables. But you can translate that in your mind to an equivalent SQL statement. So why not? We've taught the procedures, this handful of procedures, to translate the work into a SQL request that can stay on the database much more. Select these statistics from this table, group by this variable, and that'll get planned by the Hive query optimizer, and it'll run a lot more on the cluster. It'll still have to read all the rows of the table and form the groups and calculate the statistics that you've asked it for, but really only the aggregate data set gets returned back to your SAS session, and that's a lot smaller. So this is the first tip of the iceberg of moving work into your cluster, and it's not anything really new for Hadoop. This is something that SAS does with all of the relational databases, slurping all the rows out of the database across a wire into a SAS session. And just for completeness, it's available on Hadoop as well. So, there are advantages of this. We think one of the huge advantages is just it transfers your SAS skills from one environment to another. So you don't have to retrain a lot of folks on how to access data and do their data processing of a new live name statement and maybe what the address of the Hadoop cluster at your facility is. But it's pretty standard after that. It's very convenient. That shows up as a sort of a natural resource in all of your SAS work. And I like to make this, it's not really a joke, but a gateway drug. It's a way to introduce the SAS people to the power of the cluster. So they may not know why they care about bigger data sets or the availability of deeper data sets, why it's so much better to process 10 years worth of data instead of 3 years worth of data. But this is a vehicle to start introducing folks to the power of your cluster. Disadvantages, I'm sure folks already had this thought. It's like, that's not really taking advantage of my cluster. It's really just handing the work off to Hive in the cluster. Not all procedures map their work back into SQL, so you still have this problem that potentially large data sets gets transferred from the cluster through a single wire back into this. Not that many techniques have this translation effect in SQL to let the database do the work. So let's move my arrow on to the next part of the talk and say, if that's not great, what's great, right? What have we done to really move the work into the cluster? And I'd like to show this idea that we've had many talks at Hadoop Summit talking about beyond MapReduce. What could we imagine if we said, let's use the infrastructure of HDFS. HDFS runs on all of the data nodes in your cluster, and they provide calculation potential. And there's lots of examples like that, even in the talks at yesterday and today. The Yahoo guys did their talk on Storm and Spark, which is different software, some of it from Berkeley AmpLab, and Storm came from, not sure, from Nathan, but I don't remember where he worked when he did it. It's saying, let's use the cluster, let's use the data as it's partitioned out over the cluster, but let's not do it with the technique MapReduce. Let's do it with a different technique. And this idea is becoming more socially acceptable, if you like, on a cluster. You can have an idea, and that's what Cloudera did with Impala, and it's what the test project does with Hive and Stinger. It says, MapReduce got us so far, but if we could have a dedicated environment for our kind of work, and we could do things our way, we think we can do it a lot better. And Yarn says, that's fine. I can do that. You can request a list of servers from a list of resources from me, and I'll provision your process on all of these servers. And SAS is in the place of wanting something like that. please set up our network of processes on the cluster, and we'll take care of it from there. We'll access the data, and we'll do the mathematics using techniques that we found to be really useful, but integrate and share the cluster with all the other people using it, doing their thing. So I've got this one picture here, and I'll animate it here. You know, the analyst has a question, it's mathematics, and he sends it into the cluster. And there was two things going on there. Maybe we'll have a quiz on it, right? There was red dots, and they were going sideways. Those red dots represent the data that the problem was working on. And there were blue dots, and they were going up and down. The blue dots represent the communication between the mathematics as it tried to solve your problem. So it could have been a logistic regression, and of course it has to read all of the rows into the memory of the algorithm. And the red dots were acquiring the rows from the table. This is not a very big cluster in my picture here, it's only 4 nodes. But 25% of that data set is on each of the nodes. Well, we've worked pretty hard in SAS software to arrange that. That's not always the case, but the data parallelism of take the data on the server that you found it and process it in a process on that server. So the data locality is very important, but it's not the only way to achieve speed up in your mathematics. Once you've got the data, that slice of data, 25% for worker processes, they need the freedom to talk with each other to make progress. A regression, you often have a classifier variable, and you need to know how many levels of that variable. Maybe it's state, and it's roughly 52 states in that variable. Or maybe it's a zip code or MSA, and there's a couple of thousand. But it needs to allocate a unique list of how many different states are in the data set. Now, you can't be sure in any one of those slices that you've seen all the states that the total problem has. You've only seen your quarter of the data. But if you could have a quick conversation with your neighbors who are working on same problem but their slice of data, you can quickly form the complete list of all states by having a message session with each other. Whereas in MapReduce, you kind of have to shuffle that data out into key value pairs, give it to a sorter and a reducer, and then start up a second phase of your algorithm. And that's kind of laborious for many kinds of mathematics. Anything that involves iteration or convergence, that you have to try again and refine a coefficient and then see if iterating until you get to some tolerance. So the MPI is really a much better way to do mathematics, in our opinion, and forcing the mathematics into MapReduce just wasn't. This picture with a little more detail from a SAS perspective. You've typed in your live name statement, and instead of saying Hadoop, you've said SAS HDAT. SAS HDAT is the SAS binary format of SAS data as it's stored on Hadoop. If you've ever looked in a directory of a SAS session recently, you probably saw SAS 7 BDAT, which is our format of SAS data sets on a Unix system or a Windows system. So SAS HDAT is the same kind of thing. It's self-describing data with the column headings it knows all about itself. You don't have to have an external schema file to define what's in a SAS data set. And then you're going to do a technique like regression on your cluster, and how we're going to move the work there. So the first thing that it recognizes is that it's one of SAS's high-performance procedures, and that the data is out spread across the 4 nodes in the cluster. So we go and establish an MPI network. Those blue boxes called TK, which is our threaded kernel or our compute infrastructure that we want to host on each of the data nodes in the cluster to process the slice of data that lives on that cluster. We boot that up. Today we use a secure shell process and just start our process out there, but this is one of the potential improvements with Yarn. We can ask Yarn, provision these containers for us so that we can do this request. But then we can go and say, which blocks contain this data set? So rather than think of the table as one big table, we think about it as, because we want to do it in a data-aware fashion, we want to say process the blocks that are on this server. So you all know that Hadoop keeps a primary copy of the block, but it keeps a second and a third, depending on what you've set the replication factor to for safety. So you've actually got quite a few choices about which server you should process the block of all the blocks and all the servers that they're on. And we can kind of level that list out so that we process an equal amount of work on each of the slices of data. When we wrote it 10%, 10%, 10%, 10%, if it's a 10-node cluster, or in this case 25% on 4. But Hadoop might have moved it around a little bit in the meantime, and the data might have gotten a little bit lumpy. But that's okay. We try really hard to balance out an access plan or a block list to balance the work across each cluster. So that's the first step in making sure if we're going to take our room and divide it into working groups, we want to give these poor guys on this side of the room 50% of the data and let these guys loaf with only 10% of the data. So we try and make sure that we spread the work out as evenly as we can across all the workers. And that's the first important part of getting this going. So we do that optimization. We assign a block list to each server about what the other guys are doing while they get their data. There's this little animation here. You see these little red blocks. They're going, each server at the bottom is loading its blocks into the memory of that regression procedure at the same time. So we're getting data parallelism here. While this group is working on its quarter of the data, this group's getting busy with its quarter of the data, that group's getting busy in that group. They're all doing it at the same time. They're not interfering with each other at all. Most of that data is local, but they are allowed to communicate with each other. I talked about that idea that we need to form a list of states or a list of a classifier variable or any other information that we need to exchange with each other to make the mathematics calculation go faster. We have the freedom to do that because we're a MPI application. We can message, one worker can message information to another worker and they can collaborate and chat backwards and forwards to solve their problem. So they get an answer. The answer comes back into your SAS session. So the green, the SAS server function, but it didn't really do any work. It established the workers on the network, and the workers were paired with their slice of data in as optimal a way as we could configure for that given run. And we said, go do it, go do the work. Talk amongst yourself if you have to, and when you're done, give us the answer back into the SAS session. So it's very convenient as a SAS programmer because you could go to the next step and massage that data or graph it or turn it into regression coefficients for your model. But in terms of moving the work to the data, moving the work to data, moving the work into your cluster, that happens very naturally behind your SAS script. You don't actually change your SAS script a lot other than the fact that your line name happened to be pointed at a Hadoop cluster, and the software that runs in those blue boxes, the threaded kernel and the pieces of SAS, obviously that had to be installed on your cluster as well or it wouldn't work out. All right, the only thing that changed at the bottom was MapReduce. So if it's not in SAS format, how are we going to scoop up the data in many degrees of parallelism to feed the workers? So we can ask and we can configure a MapReduce job to say, go and scoop up the data on the local machine for this job and feed it up into the SAS mathematics in a fashion that's the way SAS processes its own data. So this is our opportunity to be interoperable with all other kinds of data that lives on your cluster. Right? So, old school, ran a procedure, ran on a single machine, and we've worked really hard to do multi-threaded programming, and that proc logistic lights up all the threads on that server, nearly all of them, but it's still stuck to the memory that's available in one server. So that might have been 128 gigs or 256 if you've got a nice big server. It had to fetch all the data into one server. Memory's still a constraint. On the right-hand side, this is the new way we think that computing should be done. Massively parallel. We'll use all the servers. In this picture, there was 40 nodes on the grid. Each one of those nodes didn't have a huge amount of memory by today's standard. 96 is actually small by today's standards. Most servers that you buy today have 256 or more. But even 40 nodes at 96 gigabytes is almost 4 terabytes of memory. That's a really luxurious amount of memory for a mathematics algorithm, when the previous situation it had to work with only 196, right? So it had to process a slice of the problem at a time and save some temporary results and go back to it and all that. In the new world, each worker gets handed a slice of the data and they work on that slice, and the assumption is that it fits into memory because it's not an unreasonable assumption anymore, and they get on with it. They do the work. There's no paging out to disk for temporary results as you make progress on the algorithm. It's all computed in memory. The answer is figured out by chatting amongst each other and returned to the SAS session that asked that you do the work. All right? So you might ask, well, what techniques have we converted to this high-performance architecture? So there's quite a long list here. We've been coming out about every 6 months with more procedures on this list. So if you'd have heard me give this talk a year ago, there might have been only 6 or 7 on the list. And the first procedures that we had done, not sure why that happened to me when I was practicing, and I thought I pressed the button, but apparently it's on a timer. We don't want you to copy that all down. I'm just kidding. We did the procedures, but we're continually adding more of the mathematics techniques. Of course, it's not hard, it's not easy work on our side to change the program from running on a single computer to running on a cluster. We have to rethink the algorithm. We have to teach the many workers how they're going to collaborate with the other instances of themselves, if you will, working on their data. But this is something that we're very committed to at SAS. We're moving as much of our mathematics as practical into this high-performance, massively parallel, take advantage of all the memory and all the cycles on your cluster approach that we can. And we do think this is the way forward. It allows you to process your whole data set. You don't have to sample data set down anymore. It allows you to process very, very quickly. So the picture here, scalability on a 12-core server. Last go-around of us improving performance on SAS, we focused on doing multi-threaded programming. We wanted to take advantage of all the cores in your server, but it's really, really hard work. You can make it go twice as fast on a 2-core server, and you can make it go 3.8 as fast on a 4-core server, but it taps out. On an 8-core server, you can only make it go 6 times as fast. There's just certain parts of your algorithm that won't parallelize, and there's this law known as Amdahl's law that eventually the part that won't parallelize becomes the dominating thing, and you can't get any faster than a certain amount of speed up. Doesn't matter how clever you are, this law pretty much has held for everybody who's tried it. So there's limited diminishing returns on multi-threading your code, and just hoping that the vendors, my buddies from Intel are sitting over there, that they give me lots more threads. It's not going to help if I don't figure out how to run it on a cluster. So here's the kind of damage you can do with 32 elephants, right? We built a cluster of 32 nodes, and a job that ran on a single server took 4.5 hours, ran in 2 minutes on the cluster, up of about 100, which is more than the 32 that you might assume natively. Well, if we just divide the problem up into 32 servers, how are we able to double, exceed just the scaling of the servers? Well, back to my picture, there was blue dots and red dots, right? The data parallelism got us a certain amount of speed up. The refactoring of the algorithm so that we had the algorithm, all the data in memory all the time, and we're able to calculate without doing any temporary, merge at the end. All of these things come together, allowing us to beat the scalability factor more than just the number of servers. Now, this server has 768 cores if you count the fact that there's 24 threads in each one of those. So maybe we're not doing so great. We only got 100 times faster, and yet there was 760 workers when there used to only be 24 workers. But the kinds of speed ups that you can get with the modest cluster. So imagine if you had a 1,000-node cluster, what you'd be able to speed up as you do these kind of things. That was a logistic regression. The next slide I have is a neural network. Went from 20 hours down to 4 minutes. And 20 hours is kind of a long time to run a neural network. Maybe this was a little bit synthetic. But the person was trying to prove the point that you can train a neural network, and the more you train it, the more refined its estimate becomes, or the more refined the model is. And so you let it run for more iterations. If you're not that patient, you can let it run for all day. But if you can run it on a cluster, you're more than likely to run a couple of 100 or 1,000 iterations just in the course of doing your work, rather than to schedule it over the weekend or make a special setup. So it's kind of important that this performance actually gives you business benefit, and a lot of it is just in the fact that people do more sophisticated and long-running techniques in the course of what they do. They don't have to think about it and say, oh, I'll run that this weekend and check it on Monday. It just happens in the natural course of their workday that this high performance allows them to iterate more and calculate on bigger data sets. Okay, so that was the first half of the talk, where I wanted to explain what we've done, how we've translated a lot of our mathematics to a cluster, which means making the workers work with each other. The worker only gets a slice of the data. We do this dynamic plan to try and make sure the workers and the data blocks they're assigned are on the same server as much as possible. And then we've rewritten the mathematics to work on that style, to use the MPI message passing programming technique to get the job done. So assuming that that's the case, how do you interoperate and play with all the other things on your cluster? Because I talked a lot about, yeah, we set our data set carefully in the SAS7 format, but what if my data is not in SAS format? So there's lots of different formats that your data can be stored on a Hadoop cluster. I've kind of put a handful of them: sequence files, Avro, Trevny, Parquet is the new goodness that Impala project is. It's a column store, tokenized and dictionary compressed. So there's lots of different choices for your data on a cluster. Why would I choose to store it in SAS format? Well, we do think that our format is the most efficient and blended storage format to work with SAS. We've made it very natural. We can actually just map those blocks of that file directly into the address space of our workers. We use the Linux mmap technique, which cuts down hugely on the overhead of bringing the data off of the disk blocks into the memory of your session. But you may want to keep it in a different format for other reasons. You might want to share it with other tools. You might produce it already with an open source tool chain. It doesn't matter. You get to choose which format and how is SAS going to deal with it. So this is the one crossing of this matrix, that there's two groups of ways to store your data: the SAS way and not the SAS way, the blue way and the yellow way. And you may want to process it with Hadoop tools or with SAS tools. So that's kind of overlaid that choice in the other direction. Now, I put some green check marks in the Hadoop tools with Hadoop data. That's not really the topic of my talk. There's hundreds of talks at the conference and in the literature about how Hadoop tools work with Hadoop data. And you, I'm sure, would expect that SAS tools would process SAS data, so let's not talk about that. But it's those other two corners that are the interesting ones from an interoperability perspective of, if I have my data in a different format and I want to process it with SAS, how am I going to do it? Or if I have my data in a SAS format, but I want to process it with an open source tool, am I stuck? Am I locked into that format, or am I open? Can I access that data through any tool chain that I like? So I wanted to talk about those two, the northeast and the southwest of that little grid. Data format, SAS, not SAS, and tool of choice, SAS or not SAS, right? So one of the tools, the Apache tools for data warehousing, like scripts, and what we've done, Pig is an extensible tool. You can write your own classes to extend the storage formats of Pig. So you can load at the beginning of your Pig script from SAS format dataset. That's useful because the SAS dataset comes with its own metadata. So in your Pig script, it already knows the names of the columns. You don't have to do extra work to name the columns that you might have had to if it came from a CSV or just a plain old log file. But then you can do whatever Pig script you like. I'm not a super proficient Pig script person, but you can read your data in from SAS through the storage classes that we provide, and then you can do anything you can do in Pig script from that point on. So your data is not locked up in SAS. If you want to process it with Pig, no problem. You just have to put these classes, these 3 jar files, on your class path to extend Pig with the SAS functionality, or hopefully maybe your system administrator has done that for you already and it just works. You can use Apache tools with SAS format data with that technique. And you can save it out on the other side. This first example was reading SAS data in. This example just read it from a CSV file. But you can save it as SAS. So if you already have ETL pipelines or processes in place to produce your data and you want to save an extra copy of the SAS data set, that's no big deal. You can just add it to the end of your Pig script to save a SAS copy, make it available to the SAS processing in the SAS format later. There are other techniques for working with the tools, and most of them center around the MapReduce input classes, input reader and output writer. So you may hear people talk about the SERDES or the serializer, deserializer functionality for a different kind of, thank you, 10 minutes, for a different kind of format or file factor. And this is the other kind of interface to SAS data sets that we make available. Now I say make available, we want to make this available. We have the classes and the jar files ready. We think that there's a little bit of hand-holding that goes on when we get this started. So I'm really interested if there are folks out there who have this, this need to match up their SAS format data set with MapReduce or other techniques, even Hive that uses the SERDES. I'd love to interact with you and see if we can get this concept off the air and make it work for you. But I wanted to express to folks that it's important to us to provide these open interfaces to the SAS data set so that you can integrate it with your tool chain if that's what you want to do. So I think that covers the northwest part of my matrix, where I want to process blue data, SAS data, with yellow tools, and that leaves the bottom quadrant, the southwest quadrant of this four-way matrix. What happens if I want to process Hadoop format data with SAS? Have I got a technique, or is there a way to do that without converting all of that data first into SAS format? And we do have a way. I sort of had a sniff of it in the early slides, but we have this little metadata format that describes the shape of the data that we're trying to read out of Avro or some custom format that you've written to your own liking, sequence files or protocol buffers or Trevny and Parquet, doesn't matter. You provide your own classes to map that storage format to our APIs. So you see there in this proc that gathers up this metadata, this says, oh, there's 5 columns in my data, and the class that I've written, because I'm mapping a Apache format to a SAS format to do this, is that one there, you know, ComSAS Hadoop EP input format sequence and a custom sequence file. So any kind of format that you have on your cluster that you've written translators for or serializers for, you can hook into this kind of infrastructure and feed your data directly into the SAS mathematics in all degrees of parallelism. So we will schedule MapReduce class with enough mappers to feed the worker tasks. So we're sustaining those red dots to get the mathematics to go as fast as possible. And yet it'll feed directly into the mathematics to do the calculations, the same as if we were processing it off of SAS data sets. Now there is a tax for doing this. It's never going to be as fast as the technique that SAS uses, because we've carefully laid out the data so we can literally mmap the blocks into our address space. There's almost no faster way to get that data out of the spindles into the memory of the worker process. And I really don't want to put measurements up here because I want to have that conversation with people of what it is they're trying to do, how often will they do this, you know, the pros and cons of keeping it in a consistent and shareable format versus a specialized format. We shouldn't just focus immediately on what's the cost of accessing like that. There's lots of things that go into this decision of should I leave it in a shared and common format, or does it make sense for me to put it in a special format that can work with this tool so much better? But it can cost 2 or 3 times more to read it this way. We have some examples where it only costs 10%, 15% more to read it this way. So it really depends on the kind of transformation that you're doing in this kind of a technique to read the data in all degrees of parallelism into your mathematics. All right? So, you know, this picture, we saw it before, except at the bottom, instead of finding the block list and doing this selection, I don't know about this format that you've written a class for. I'm going to let you take care of all of those details. I'll schedule enough degrees of parallelism in the MapReduce job that your code will feed that many worker tasks in SAS, and the mathematics will proceed almost unaware of it. It might notice that the data is coming out a bit more slowly than it does from a SAS format, but it's still operating at massive scale, at a cluster scale. There's as many workers as you've allocated to the job, and that's how it proceeds. All right? That's that. So I feel like we've got to check in all of those quadrants. SAS with SAS, of course, Apache tools with Apache format, of course, but the other two, when it's Apache format but SAS processing, or it's SAS format but Apache processing, that was the main thing that I wanted to bring out, is that we do have ways to interface with data on all axes, on all corners of this quadrant, something that you should make sure of if you're looking at a tool to work on your cluster. So, you know, last slide is on we're a big enterprise now. We've got one of everything in our data center. We've got a Teradata machine in there. We've got an Oracle Exadata. We might have a Greenplum. They all have many degrees of parallelism, many lanes to get the data off the disks into the processing. We've got a Hadoop cluster. We've got some mass servers They all live on a nice InfiniBand network or a 10 gig network that allows these servers to talk to each other. What's the best place to store everything? How do I keep this all together? You know, that's a very, very contentious subject. Some people are on the journey to replace their enterprise data warehouse completely with their Hadoop cluster. I think most people are of the opinion that they're going to use both for the meantime, and use the one that excels at what it does. You know, make a choice about which one should we use for what. So the Hadoop is really good at the cost of storage. It's 10 or more times cheaper per terabyte cost advantage. It's much better at data sets that you don't yet have a schema for. There is no structure, so you're trying to assert the structure. The thing that we really like about it is that a 10,000 column table, no problem. So when you're doing analytics and you've got a bunch of data and you don't really know which is the signal and which is the noise and which patterns are useful, and doesn't matter. You can throw all of them into the initial stages of the exploration, whereas getting 10,000 columns in your Teradata or your Oracle is impossible. They have limits. You can only get 1,000 columns practically in a relational database. Some of them let you go all the way to 2,000, but none of the relational databases let you get 10,000 columns in your table. So for exploratory analytics, Hadoop is fantastic. You can grow your cluster. Growing your enterprise warehouse a bit more expensive, and you've got to go and visit the finance committee a bit more often. But we do find this conversation happening where people say, Hadoop, that's my discovery, that's my experimentation, that's where my data scientists go and build models. Enterprise data warehouse, and that's where maybe I do keep my customers and my campaigns, and I run the optimization to allocate customers to campaigns. That's my line of business data. I keep it in an operational system. So there is this divide. The SAS mathematics actually doesn't really care. It'll run in all degrees of parallelism on an enterprise data warehouse class. It'll run in all degrees of parallelism on a Hadoop cluster, and sometimes it's just a different kind of mathematics. You're doing optimization on structured and cleansed data, and you're doing variable selection on random data, you know, stuff you still haven't figured out, things that you're having questions on. So that's my talk. This is the picture that I wanted to leave you guys with. This is the really hard work that the programs have been doing. Do two things: the red dots, the data parallelism, and the blue dots. Improve the performance of the algorithm by having these conversations with each other as you proceed on the algorithm. And that's the work that we've been doing into, it takes a company like SAS to really commit to doing that. And that's the thing that we think puts our performance an order of magnitude above the folks who took their algorithm from the single machine and said, we'll just run several copies of it on a cluster. All right? So last question, which Hadoop distributions? So we started with Apache 2.0. Cloudera, of course, got there. You'll see everybody on that list. We work with Horton 2, but none of you guys run that yet. That's still in beta. We're so close to working with Horton 1.3. I hope within a couple of weeks we'll have the last few patches landed that we can run on a HCP 1.3 cluster. We work with our other partners, Pivotal, MapR. We've got plenty of work to do to work on MapR. We're very close to working with Intel's distribution, so we're to the point of working on 2, and so there you have it. These are the mainstream Apache distributions, and obviously that makes sense to you. If you're choosing and yours isn't on the list, then what are you going to do about that? What is SAS going to do about that? So that was probably the talk. I had 6 seconds left. I'm sorry, that leaves one question perhaps. I will hang out outside the room there and field people's questions. We do have a booth here at the conference, so come by and see us there. Thank you very much for your attention.